Welcome back. We're going to look at another problem now. This problem is problem C6 in Pinter's book. This problem states that, sorry, I need to have my pen, handy dandy pen, that if G is an abelian group, we let HP be the set of elements of G for which the order is some power of a prime P. The claim: HP is a subgroup, and in particular, it's a normal subgroup. And G mod HP has no elements with orders any power of P. And I like this problem, although I'm not sure that the primary application of this kind of reasoning is something that you guys are likely to encounter in the near future. But I know I've seen this kind of construction appear in geometry, in particular when one studies elliptic curves. One is often interested in studying reductions, mod P, and looking at the P subgroups of elliptic curves. And I know you guys don't know what those are. But so when I saw this, I was like, this is a great problem because it's a relatively elementary problem and it's something that actually gets used. So I thought I would show it to you. So first, let's do that HP is a subgroup. So for HP to be a subgroup, we have to prove the usual collection of facts. We need the identity element. This is obvious because in particular, e to the p to the 0 equals e to the 1 equals e, and so therefore belongs to HP. We need inverses, but if G is in this HP, then G inverse has the same order, which is the same thing as saying G inverse is in HP, right? This is some kind of, power of a power, and if it works for G, it works for G inverse. The only one that's non-trivial is closure. And so for that, let's say we have a G1 and a G2 in HP. And let's say that the orders are P to the M and P to the N, respectively. Then I'll write K for the max of M and N, just because it makes the notation a little bit cleaner. And if I do this, then now to show the closure, we can write G1, G2 to the P to the K. And using the fact that this is an abelian group gets me to here. And well, for one of these guys, it's just E on the nose. But for the other one, we can break it off. So let's assume that without loss of any generality, that M is greater than N. Maybe maybe I shouldn't have written K. What am I trying to say here? What I'm trying to say is one of these things, this is the order, and so it's E. For the smaller of the two, I picked a smaller power of P. And so this differs by some other power of P, like maybe it's K minus the lesser of the two. But in either case, since it's the lesser one and the lesser power divides the greater power, both of these things are also E. So you get E. All right. Why is it normal? Because G is abelian. When you have an abelian group, every subgroup of an abelian group is automatically a normal subgroup. So nothing wrong here. Okay, for the next part, I need a theorem from Pinter. So let me just grab this theorem and let me put it up on our board so we can remind ourselves of the statement. It's theorem 5, which I don't think we covered in the videos because we only have so much time, and also reading you the textbook is boring. Theorem 5 says two things. It says if HA equals HB, actually I could say it's not just if, it's if and only if AB inverse belongs to H. And the second condition, HA equals H, which is the same thing as HE, if and only if A belongs to H. And I've actually been using like this kind of reasoning previously when talking about absorbing elements into cosets. And so probably that was a little bit of a blunder on my part to gloss over this. But in any case, we have it here now. And so with this theorem, we can apply this theorem to our problem as follows. So let's recall the statement we have to prove. We have to prove that G mod HP has no elements with any order, which is a power of P. So we'll do a sort of a proof by contradiction for that part. So we suppose we have G in G mod HP. And also let's suppose that its order is P to the K. I shouldn't probably write G. It's a little bit confusing what I'm saying because I was using G for elements of the big group. So I should probably either write G or like in square braces for the equivalence class, or just change letters altogether. Let's change letters altogether. Let's use A. Pinter likes to use A a lot. So we have A in G mod HP, and let's say that A has order P to the K. Now, we know how to calculate HP A to the P to the K. That is HP A to the P to the K. And since this is the order, this is HP E, or simply HP. Because of the theorem, this implies that A to the P to the K belongs to HP. And at this point, we're pretty close. How do I say? This means that this element, A P to the K, A to the P to the K, must have itself some prime order, some prime power order, maybe P to the M. Probably, right, worth specifying. This tells me that A to the P to the K to the P to the M equals E, but this is the same thing as A to the P to the K times P to the M. And now by doing just a little bit of algebra, this is A to the P to the K plus M. Did I do that right? Should be. But you see, this is itself a power tower. And so because A to the power of a P power is the identity, and the order of A and G has to divide this P to the K plus M, we see that the order of A is a power of P. And therefore, this A lives in HP. So therefore, last step, the coset HPA equals HP. And so essentially we're done. Okay, this took a little bit longer than I thought. I thought this problem would be super short and slick. I don't want to say that it wasn't slick. It wasn't the worst, but there was a little bit more symbol fidgeting than I thought. So I think I'll leave it here. We'll do one more problem before we call it for this section. We'll look at section E. So hold that thought. Be right back.